Have you ever had the professors where they like, we need to meet more times, and so let's meet this weekend and let's meet in the evening and all that? That's good. All right, so are there any project questions before we get going? Jared's email was helpful? What? You're killing me, man. You're killing me. You're not signed up for the Google group and getting all the help? You're handy. Holy crap, dude. Why not handicap yourself? I'm going to go run a marathon, but I got to put 50 pounds on my back. All right, no questions on projects? Okay, so let's talk about noise shaping topologies. And so we've covered what order of topology? First and second. Yeah, first and second. And so now we're going to cover higher order topologies, which would be, so just give me for third order delta sigma modulator, what would the noise transfer function look like ideally? Right, third order differentiation. And the problem is, what? You get first order, you get this. Second order, you get this. Third order, you get more noise. So stability is a big issue. Does everybody follow that? Okay, so if we look at the implementation of an nth order noise shaping modulator, first off, what do you notice? You notice that I've got to have non-delaying integrators, and the whole point is, if what I'm trying to get at here is that you remember our block diagram where we have this and we had A of Z, and we'll put A of Z in here, and then we had the quantizer, and then here we had our B of Z. To get a higher order modulator, what we want to end up with is an A of Z, which is equal to Z to the minus 1 all over 1 minus Z to the minus 1 to the mth power. So mth order modulator. So let me just make sure I'm recording here. I know I'm paranoid. And then B of Z is then equal to 1 minus Z to the minus 1 to the mth all over Z to the minus 1. And the issue here, and so this gives us a noise transfer function of 1 minus Z to the minus 1 to the mth power, and a signal transfer function of what? Z to the minus 1 delay. Same as we've had in the last two. But the problem is, you look at this and you've got non-delaying integrators, so non-delaying, non-delaying, and then your last one's a delaying. This becomes practically difficult to implement, okay? So we're going to talk about that. You can't, basically. We all know that you can't. You can't get a switch capacitor circuit to make the input go from here through a bunch of integrators with no delay, because you've got the switches bouncing back and forth. So you have to have a delay through each of the integrators. Does everybody agree with that? Does anybody agree with it? And so if I go look, just to make sure it's clear, if you go look at the different inputs, you might say, oh, well, what about this one right here where, oh no, I can't use that one. Why can't, let me adjust so you can see better. Okay, I can't use this one because it only has one input, so I've got to use these two this where V1 and V2 are both inputs, and this would be the fastest delay where I'm connected to Phi2 to minimize the delay. And so my Phi2 switches would be used here and here. Now you might also look at a topology like this, but of course you still see we have delays even though we're messing around. And there's actually one we'll talk about later in this chapter, probably next lecture, that is, let's see, where is it? Where did that bugger go? Here. Here. But again, if you cascade these, the Phi1 switches in the next stage keep it from the signal from going all the way from the input past it. So there's no way to do a cascade of non-delaying integrators. Does everybody follow that? Okay, so if I go back now and I ask, all right, well, if I could do a cascade of non-delaying integrators, what would be the result? How would I benefit from that? How would I improve my performance? And you can probably guess in your mind, for first order, we had how much increase in SNR for doubling and effective number of bits for first order? Yeah, 1.5 bits for every doubling, which is how many dB of SNR? Okay, 1 bit corresponds to how many dB in SNR? 6. So 1.5 bits is 9. And then for second order, we had 2.5 bits, or 15. For third order, we have 3.5 bits and 21 dB, right? Anybody, if you don't learn anything, make sure you follow that in the class. So if I said you need a 1,000 to 1 dynamic range, how many dB and how many bits is that? 1,000 to 1 is 60 dB. How many bits? 10, yeah, roughly. Okay, so if you look then, So let me cut to the chase here. So it says that the equation shows that every doubling in the oversampling ratio k, the resolution increases by m. So if m is 1, first order, we get 1.5 bits, m is 2, 2.5, m is 3, 3.5, etc. And here you see what I talked about a moment ago. That is the noise transfer function. What's this term right here? What is this term right here? Yeah, the quantization noise for like a Nyquist converter, right? That's the white noise that's spread evenly out over the spectrum. And then here's our increase I talked about, that at high frequencies it goes up and we get problems with stability. Here it shows, oh yeah, so if we increase our SNR, we get just what we said a moment ago for, 3 bits or third order noise shaping, we get 3.5 bits increase, which is 21 dB. All right, and then here is what we talked about, the noise transfer function, the A of Z and the B of Z. And then following, we get what is the topology look like, and it's seen right there. So then you might ask, well, how do I filter the output of the modulator? And there's no surprise that for the filtering, you get L equals 1 plus M. And what is L? Order of, sink filter. Any questions? And just prove it that we discussed that. If you want to see the math, you can see that M plus 1 equals L, sink averaging filter. Any questions there before I talk about how you would actually implement this, because this won't work, right? So if you attended the dissertation a few weeks ago by Dr. Kong, now doctor because she passed, you might have seen a topology that looks something like the following. Here you can use standard DSP techniques where I'm feeding the signal forward into the adders and I'm feeding the signal back to the adders and subtracting. And tell me, okay, so you might, in your DSP class, did you go through like canonical forms of digital structures? This looks like one of them, right? Where you got your A's coming in and your B's being fed back. What does canonical mean? Or canon? It means the proper way of doing things, right? The right way, where you don't have, what's that, minimal? Yeah, minimal hardware. Here, if I look at this and I ask, tell me intuitively, how come I can make this stable? Don't use math. Just tell me, how can I intuitively look at this and make this stable? How do I know I can make it stable if I put in a topology like this? What's that? You don't have a race? Yeah, so, right. Well, the way I think of it is you're minimizing the delay in the forward path. So you don't have as much delay going forward, so it's easier to stabilize the system. And the the example I gave was driving the car. The forward path is the me watching the road. Well, if I add delay in that path and something steps out in front of me and I've got a delay in reacting, well, I'm going to hit it. I'm not going to be able to respond fast enough in that feedback system, and me hitting the brakes will be unstable, right? So on your projects, think about this. If you're implementing a second order modulator or trying to implement and you're having problems with stability, what you might try to do is to take your input and feed it forward into the next stage. Okay? The problem there that you have to be aware of, so here's with the single feedback loop here, because Jared and I played around with trying to get this to work last night, and it's very tough with the second order. You got it working though, right, Costas? The second order topology? Oh. Oh, okay. Well, what you might try to do is, but again, you have to think about this because this stage is inverting, is you might connect your input in and try to feed in directly to this point. So you have to derive the equations for it, but feed directly into this point to try to give a better, bypass the delay of the first integrator while still getting kind of second order improvement, and I'll talk about that more. So the key point is I'm going to put this signal in, I'm going to put an input here, feed it forward to try to minimize the forward delay to make this stable. Now, you might ask, why would we want to do that? Well, one reason you want to do it is because you can borrow things from DSP, so you don't have to reinvent the theory of DSP. Okay. The other thing is, if you look at the end result, here's what you get with using M differentiators. You get this increasing and going up, and the bigger M is, the faster it goes up, as we discussed, right? Well, if you implement the feed forward with those coefficients, adding the B's in, then you can think of that as low-pass filtering the differentiation. So your differentiation, this thing continues to go up, but if you low-pass filter it, it means you're passing, say 0 dB, you're passing this transfer function, the noise transfer function, through something that does this. And then it kills the gain at high frequencies. Okay, so this would be LP F of Z. Okay, and it's that straightforward. Now, I think you can implement that or use that in a second order continuous time. But again, nobody's done this, so I don't know what can be done. It's not like I'm giving you a project that somebody's done and I know it can be done. So you got to keep that in mind. All right, are there any questions on the basic idea? And a lot of times if you put a filter with a ripple here, if you've taken digital filters, then your noise transfer function has an undesirable ripple, but that's still fine if the ripple's small. Like if you have a small ripple, it can still be something that's very useful, okay? What I want to do is I want to talk briefly about implementing the A and the B in the feedback coefficients. What I would do if I were you and you were trying to apply it towards your projects is I would take the topology like what is seen here. I would put a resistor going forward to this path, and I would think about it and say, okay, if I put a positive going voltage here, that causes this node to go down. Well, at the same time, it's going to cause a current to go in the opposite direction. Is that going to improve or make the stability poorer? So something to think about. All right, so let's talk about how you select these coefficients here, the A's and the B's. And there's a ton of software available for doing digital signal processing. So if you feed forward the coefficients, remember our A of Z before? It was this. A of Z is Z to the minus 1 and B of Z was this. If you feed forward those coefficients like we showed, then your A of Z becomes this this transfer function here, which ends up summing to, let's make it a little clearer, which ends up summing to this equation here. And you can, like I said, use standard DSP, and then you can simplify it to have this shape right here. So let me pause for a moment and ask you, if I wanted to just, without a computer program, get an estimate for the A's, tell me what you can do with just pencil and paper looking at this. How to select the A's and how to select the feedback or the performance to get that low pass response. What could you do? Okay, so let me ask a simpler question. If I want to approximate, I'm doing a frequency response, and I want to approximate Z to the minus 1 over 1 minus Z to the minus 1 for a frequency response, not in the Z domain, what do I do? What do I use? Okay, so let me back up because this question's super easy. If I want to, so I'm trying to design a low-pass filtering for the transfer function. And I know my A of Z ideally is equal to Z to the minus 1 over 1 minus Z to the minus 1 to the nth power. And then here my A of Z is equal to the summation of I equal 1 to M of A to the I power times Z to the minus 1 over 1 minus Z to the minus 1 to the M minus I plus 1. Okay, so let me pause for a moment and tell me what the A's are for these two to be equal. All the A's would be 0 except A1. So I would be 1. So there'd only be one A, and that A would be equal to 1. Okay, does everybody see that? I'm saying something super simple. I'm just saying, oh, A1 is 1 and all of these are 0. Then my input comes in and it's exactly the transfer function I showed you a minute ago, correct? Okay, if I look at this and I go, okay, well, I want to design it so that I low-pass filter the input. Tell me how I could approach this problem. I'll start you out. Let's write it as let's write the ideal. Yeah, there's so many ways of doing this. We could write it as z to the minus 1 over 1 minus z to the minus 1 times m, and then plus summation of I equal 2 to m a to the I times z to the minus 1 over 1 minus z to the minus 1 to the m minus I plus 1. And then the case we just mentioned, all these i's are 0, and so this is equal to this. Or whoops, I got a mistake here. What's that? Yeah, I was assuming A1 is 1, but then it doesn't work out because if A1 is 1, I still am using delaying integrators in all of these. I'm getting off topic here about my point. My point was, if I want to go from I'm not going to use a computer program, and I want to go from a z to the minus 1 over 1 minus z. I want to write this. This is one thing I don't want you to go in the class, because you take DSP and you take all these classes and there's lots of z domain crap and all this stuff. I want you to have an intuitive feel. How do I write this in the frequency domain and why? Tell me how to derive it. What is this in the frequency domain? No. It's easy. What is this called? A circuit that implements this transfer function. An integrator. How do I write that in the frequency domain? There's one way of doing it, right? With an op-amp. That's how we did it in continuous time. Let's prove it. What is the transfer function for this integrator here? That's what we're using instead of this, right? So how do I prove that in this equation here? What is z to the minus 1? Wenlan. What is that equal to? Correct? Okay, so tell me how I get from here to here. So I should say approximately, because this is periodic, repeats at f sub s, and this isn't. This is just for low frequencies. So how do I get from here to here? We went over this. What do I do? Taylor series expansion, and that ends up being right? Now you could argue, oh, well, there's an inversion here. Okay, there's an inversion. Okay, but then I plug this z to the minus 1. I guess there isn't here. In the direct translation, there is here. And what do I get? Well, I can multiply top and bottom by z, and I end up getting 1 over z minus 1. I plug this in for z. I guess I do get the inversion. And I get 1 over j omega RC. Or 1 over j omega f over fs, and then I just simply say RC equals f over fs. Is that ringing bells with anybody? So the point is, I got a bunch of integrators. If I want to get an idea for what this is doing, I replace this term with 1 over j omega RC. Then I can adjust the RCs depending on what the value is, and I can actually lump that in with the A. And then once I've got the A lumped in here, I've just got a addition of a bunch of integrators that I'm going to add to try to give me this low pass response to get this filter here. Did I lose everybody on that? Okay, so the key takeaway, we're not going to spend any more time on this, is that you want to kill the noise at higher frequencies. If you want to try to apply this for your project, make sure that you're derive the transfer function and make sure that it's not going to make it more stable by putting in a signal that doesn't that's in the wrong polarity. I don't know, I'd need to think about it. Are there any questions about this? How about this? Was something I want you to know, that z to the minus 1 over 1 minus z to the 1 is an integrator. You can use z is equal to, to get, this is how I think of it when I'm looking at, like, somebody in digital signal processing will throw up some equation. I'll be like, what the hell is that? So I always say z, that's approximately 1 plus j omega f over fs. Then I can plug that into the formula, and I get, it doesn't work past f sub s over 2, right? Because it repeats, it swings around the unit circle. But then in my mind's eye, I can figure out what the filter transfer function is. Does everybody follow that? Because at least for me, when I was taking digital control or DSP or whatever, you get these ridiculously crazy looking Z domain transfer functions, and you'd be like, what the hell is that? And I had no intuition whatsoever what was going on. Okay, and then by plugging in this, I could get some idea. Does everybody understand the limitations? Only because it's a Taylor expansion. And what's the third term for the Taylor expansion? This squared divided by 2 factorial, so it only works for f much less than f sub s. Okay, and it starts to deviate, but I mean, for most practical cases, it works well. Any questions before we move on? All right, so the next thing we're going to cover is multi-bit modulators. And so you might ask, why can't I replace the quantizer with something other than 1 bit, 4 bits? So then my SNR is going to 6.02 times n, which is the number of bits in the quantizer, plus the increase due to oversampling. Does everybody see that? And so now tell me, based upon what we've discussed in class, before we do an example here, what's an issue with this? Why did we use a 1-bit ADC? It's linear, right? You still get the feedback signal here, but it's perfectly linear. So if I look at the transfer, if I draw the transfer characteristics of the DAC, here's V out, here's V in, and then I get something that looks like this. So this is, say, VDD, and this is 0, and then this would be VDD over 2. And then I ask, all right, well, draw the points. If my input's swinging like this, I have some gain given by the slope. If my input out of the op-amp is swinging like this, I have another gain. Does everybody see that? So now if I go to a multi-bit ADC, what I end up getting is something that looks like this, right? So, and you could shift it to get the 1/2 LSB, but then I get a curve that looks like this. Well, now if I try to change the slope, if there's any nonlinearity, it's bowed or whatever, that's going to come out and limit my performance. Does everybody see that? Now, so let me do an example, and I want to talk briefly about random element, dynamic element matching, because this is a very, if you go do anything in multi-bit delta sigmas, which a lot of people do, because you can use like 4 bits and you can get better performance because you're starting from 4 bits. You need to know about random element, dynamic element matching, and so I'm going to spend briefly a slide on that. But before I do, let's go download some examples and wake everybody up Friday, no lectures this week. First one, whoops. Has anybody ever seen that sign before? I can't, whoops. Where are we? Actions, implementing. How come I didn't put a zip file for that one? That's fine. Let's go get it in chapter 7. You wouldn't be surprised how many emails I get from people that say, hey, you have a broken link. And so I respond, you mean the broken link that I'm going to record next week? Oh, yeah. So that's why I put the big red sign on there. If a link is broken, but I just took it off. So, yeah. So there, does everybody see? And I'm using the output of the DAC as my output so I can see what's happening. And then you see, oh, okay, there it is. Yeah, it's better. It's a 4-bit DAC, okay. All right, so there's a couple issues here. Does everybody understand the basic idea? So the average you feed back, but it's closer here, but it's not 1 bit like we had before. So the issue here is mismatch. So, well, let me ask a question. If I were, so I'm going to ask some really simple questions. If this is an A used for A to D converter, where do I take my outputs? Where's the output of the circuit? Yeah, output of the ADC, just like always, right? These are the outputs. Those go to the digital filter. Does everybody follow that? Okay, this is the feedback loop. So if I ask you, which is more important, the performance of the ADC or the DAC, and why? The DAC is more important, right? Because errors in this are in the forward path, right? They get suppressed. But the feedback path here, that needs to be precise. In my analogy, that's me taking the cup of water out. I can make mistakes with the ADC, but when I take that cup of water out of the bucket, here in my DAC, putting the signal back, it has to be precise. So now here's the problem. If you can make a precise DAC, and it has to be as precise as the final resolution. See, that's easy to do with 1 bit because you get 0 volts or 5 volts or whatever your VDD is out. If you have to make a 4-bit DAC that's 10-bit accurate, well, you're kind of defeating the point of using noise shaping techniques. So you need this to be, oh, I need to take the water out within 10-bit accuracy, right? It's easy with 1 bit. It's empty or full. It's not easy with a multi-bit DAC. They use what's called dynamic element averaging. Okay, and it's very, very common in these noise shaping converters, and so I want to make sure everybody follows. It's very simple, but okay, so I want you to imagine that, let's do 2 bits or 4 converters. So I have the following. I have 10 microamps, 10 microamps, 10 microamps, etc. And then I've got my output here. And then I've got switches that go down, and we'll call this D0, D1, D2, D3. Okay, so my DAC is 2 bits. There's a B1 and a B0. Okay, so here's where I cringe, because when I go over this, I went over something similar in my digital class earlier today, and I'm like, they don't know basic digital logic stuff. Okay, so here's what I want ideally. B1, B0, and then out. So I got 0, 0, 0, 1, 1, 0, 1, 1. Okay, so if I have the output is 0, 0, let's say, I get, you might set it as 0 here. I'm going to set it as 10 microamps. Then if I have 0, 1, I'm going to get 20 microamps. If I have 1, 0, I'm going to get 30 microamps. And if I have 1, 1, I'm going to get 40 microamps. So what's my LSB? Yep. Okay, so you could say, oh, I'm going to close this switch if I have 0, 0. If I have D1, I'm going to close both of these, etc., right? The problem is that if these don't match right, like this is 9, this is 11, this one's 9.5, this one's 10, then you can get a constant error, meaning if I have one of these on or two of them on, I'm constantly taking the wrong amount out of the bucket. Does everybody follow that? So what I can do instead is I can randomly change which one of these switches are closed. So for example, if I were constantly putting out 20 microamps, I might start out with this one and this one closed. Then the next clock cycle I might do this one and this one. The next clock cycle this one and this one. Does everybody follow that? And so by randomly moving which one of these things is connected, even for the same input code, I'm going to randomize the errors, and that's called dynamic element matching, and it's very common in multi-bit converters. I'm going to show you, sketch a circuit on the next page, but before I do, are there any questions? All right, no questions? All right, so what I want to do is I want to randomly select which one of these bits are closed. So I have basically a thermometer code that comes out 1, 2, 3, or 4. So I want to randomly switch this. I can just sketch it here. So if I look at this, I might, let me see, where's a good example of, think of doing this. So if I take, here's my outputs. So we'll call this out 1, out 2, out 3, out 4. And you might put a switch here that connects this up like this, and a switch here that connects this up like this, and then you have a control for those switches, which is a 0 or 1. And so when it's 0, oops, I need another switch here. When it's 0, this switch is closed and the output goes here, and this switch is closed and the output goes here. And then when it's 1, this switch opens, and I switch the outputs here and here. Does everybody follow that? So I then can take and randomize this and have a counter that generates the codes that randomly connects how these are put together. I don't want to spend, I'm going to show you one more example, but before I do, are there any questions on this? Because I don't want you, when someone says, oh, you use dynamic element matching, DEM, I don't want anybody to say, DEM, I don't know what that is. It's very simple. It's just randomly selecting your unit elements. It only works with unit elements to feed back and randomize errors. So if I have a large number of these and I randomize it really well, then the mismatch is reduced. The variance of the mismatch is reduced, if it's Gaussian, by the number of sources or the number of unit elements. Does everybody follow that? So I'm saying nothing more than when I looked at the quantization noise in time, if it has a Gaussian distribution, then the variance is, whatever it is, sigma squared we'll call it, is reduced by the number of points I average. Or the standard deviation is reduced by the square root of k. I'm just repeating the same old thing. Any questions? Okay, I want to show one more example here, but it's just randomizing the feedback. The last example I'll show is right here, which is just showing some resistors here, and then you have a decoder which comes in and a counter that changes, and it just selects which one of these taps it goes around. And so what happens is the VDD and the ground positions change in this resistor string, and then you just randomly select various taps as the decoder's running the VDD and the ground around on the string. Okay, so you just randomly select where the tap is, and then it randomizes the mismatch in the resistors. Okay, any questions on, so the takeaway, if somebody says, what's the drawback of using multi-bit converters? Linearity in the DAC, because it's not a one-bit DAC. How do you get around that? People use dynamic element matching using randomization of the unit elements in the DAC. Any questions? Is it good? All right, as good as it can be Friday. Would it be evil if I asked to have a makeup lecture next Friday, the Friday after Thanksgiving? I don't think I'll come either, but you know, if I'm not scheduled to miss any more days, but if I do, I'm going to be like, you know what? I don't think it's bad if I miss a day at this point. What's that? Nah, no. Well, you notice when are the projects due? The Monday of study week, right? So that you have other time to work on other classes and stuff. I don't want you complaining, Baker class is killing me. All right. So the last topic of the day, I think, is going to be error feedback, and it's a pretty important topic. Where are we? We're higher order modulators, filtering the output, Ooh, I'm ahead of the schedule. We could quit because I just went through multi-bit, and now we're doing error feedback. Woohoo! Now I want to do error feedback because we have time, and maybe we'll do cascaded, and I'll move all this down here. All right, because we still need to do band pass and get into chapter 9 a little bit. So here is error feedback topologies, and so these error feedback are used for pure digital implementation of noise shaping. So that's useful for doing digital to analog converters, okay? So here's the thing. Imagine you have a digital word that comes in here, and it's got a high resolution, say 10 bits. And then what's the output is a 1-bit code, for example. It doesn't have to be. And then you take that 1-bit code that's running much faster, and then you filter that, and that generates the analog signal. Now, just to cut to the chase, why can't I implement error feedback in analog systems? And it has to do with this subtraction in the feedback loop, where I can't do this precisely, and since it's in the feedback loop, if we make mistakes in the forward path, right, those are less of an issue. But if I make issues in the feedback path, that's a big problem. So let's go through and determine the transfer function of this circuit here, and then we'll talk about implementations. So tell me what to do. All right, so let's define that. Let's call it what haven't we used? X, Y. How about X? V out of, well, hold on. So if I define this node as X of Z, what is V out of Z then? Oops, X of Z plus VQE of Z. And then if I look at that, what is this node? It's labeled there, right? It's VQE of Z. Because I'm subtracting X of Z from here, which gives me VQ of Z, right? That's the beauty of doing digital modulators like this. So then this node is right? And so then I get X of Z is equal to Vn of Z minus Vq of Z times Z to the minus 1, or V out of Z is equal to VQ of Z plus Vn of Z minus VQ of z times z to the minus 1, or v out of z is equal to v in of z times vq of z times 1 minus z to the minus 1. And you should all recognize, where do I point to the noise transfer function? Boom. Signal transfer function is 1. Okay, so does everybody see this? So now, here's the thing. How do I implement this subtraction, and how do I implement this quantizer? The way I do that, if I had 10 bits coming in here, is I get rid of the lower 9 bits and I only use the most significant bit coming out. That's what a quantizer does, is it gets rid of information. So if I have a 1-bit output, I'm going to chuck or get rid of the 9 bits. I'm going to remove those and only have 1 bit coming out. That 1 bit then is added, or the input to there is added to the or subtracted from this signal, and basically this is just the lower 9 bits. So it's super simple to implement, which I'm going to show you in just 2 seconds. Okay, any questions? Yeah, you got to clock the quantizer faster. So this word's coming in slow. This is clocked quick, so you get a real fast 1-bit output because it's oversampling. That 1-bit output then is filtered, and that gives you your analog signal, just like we're used to. And the concept of 1010 and filtering at this point shouldn't be foreign. It should be very straightforward, I hope. Yay? I mean, probably before the class, if I said you can take 0 or a 1 and get an analog signal out of it, you would have said, no way. All right, now hopefully you say, oh yeah, I can do that. All right, so before I cover the implementation of this part, let's talk about second order noise shaping and derive this transfer function for that. And that's seen right here. And so would everybody agree that I could label this point what? So, yeah, VQ. I mean, it's the same argument. Could go through it again. I don't think so. So this is z to the minus 1 times VQE. And this is z to the minus 2 times VQE. And so what I get is 2 times z to the minus 1 VQE, which is this path. Or whoops, minus I should say. And then this path would be z to the minus 2 VQE of z. And that's plus Vn of z plus VQE of z is equal to V out. And so then I can write V out is equal to Vn of z times, and I'm going to write it verbose just for this first, VQE of z times 1 minus 2 z to the minus 1 z to the minus 1 plus z to the minus 2, and that's equal to Vn of z times VQE of z times 1 minus z to the minus 1 squared. Can I get a second on that? Good? So there you see, okay, that's how I implement the second order error feedback using all digital techniques. Okay, so I got a question. Why not just use interpolation? What am I getting out of this? So I got a word coming in here. Let's say it's coming in at a megahertz, and then say coming out I get 128 megahertz 1-bit word. And all those equations we talked about still apply. Why? Okay, so first off, why would I want to do this? There's no errors here, right? Because it's all digital. Coming out here, it's 1 bit, perfectly linear. Okay, so it gives me a D to A. Can I do this same thing with using interpolation? Tell me, just as a sanity check for myself, because I'm assuming everybody knows, what were the different methods to interpolate? zero padding, hold register, linear interpolation, but all of those don't output a 1-bit code, right? That averages to the input. Okay, so this does that. And then we can filter this out. And so you might have some situations where you want to transmit information. Well, if you transmit 1-bit code, that's a lot easier than transmitting 10-bit codes, but you have to run it quicker. Okay, are there any questions? Because I want to talk about this part right here. Okay. So how do you implement that part? And the answer is you have to make sure you use 2's complement numbers and you don't do your arithmetic wrong. But basically, you're taking this whole thing here, where you got your quantizer, your subtractor, and all that, and you're implementing it with just some wires. So you're taking your output, you're subtracting off a bunch of bits. Let's say this was 10, this was 9, then this would be 1, and you're just feeding it back. Okay, does everybody see that? So let me give you an example. If I wanted to implement this with 2's complement numbers, then I would say, okay, I'm outputting here a 1 is a negative value and a 0 is a positive value. Then what I'm going to feed back here is the subtraction. I'm going to remove the MSB from the circuit, which means I'm going to do what? If I'm removing the MSB, if I have a word, let's just pick out a 4-bit word, 1 0 1 0, which is what in let's live it like this, which is, let's do 5 bits. What is that in 2's complement? 10, right? Does everybody agree with that? 1 2 4 8, correct? If I go say I want to remove the MSB, I want to get rid of this, then I want to end up with, basically I want to strip this out. I want to end up with what? Removing this. Yeah, I want to get 2, right? So I want to end up with 0 0 0 1 0 because I've used the MSB. I'm subtracting, right? Does everybody follow that? So now if I look at this word, if I want to come back and subtract it or add it to my 10-bit input, well, I really want to keep this as 10 bits and just feed all 10 bits where I know that the MSB is no longer there. Does that make sense? No? So, okay, so let's just use 5 bits instead, right? So I have coming in here, I have this number, 0 1 0 1 0, okay? I strip off the MSB, which means I feed out a 1, and then I feed the output word back, and I subtract this from this. So I have to keep the word size the same. Because it's, I'm sorry, what do I, 0, I feed a 0 out, sorry. Right? And then I get rid of this bit. Yeah, you're left with, after you get rid of this, you're left with 0 0 0 1 0. So you get, because that's your quantization. You're saying I'm getting rid of whatever this MSB is. So let me make it simpler. If I have, no, that's the sign bit, right? So that's the one I'm outputting. Well, hold on. Yeah, I'm outputting the sign bit, 0 or plus 1. So let's do 4 bits. So if I do 4 bits, I get 0 0 0 0, which is 0, right? And I get 0 0 0 1, which is 1. I get 1 1 1 1, which is minus 1. And I get 0 0 1 0, which is 2, all the way up to 0 1 1 1, which is 7. And all the way down, we'll get 1 1 1 0, which is minus 2, all the way down to 1 0 0 0, which is what? Minus 8. Does everybody agree with that? Okay, so these are my numbers. I'm going to, if they're above 0, I'm going to subtract the maximum amount. If they're below 0, I'm going to add. So everybody, okay, does anybody have any problem with this? Okay, so my quantizer says, is it above or below the common mode voltage? If it's above the common mode voltage, I'm going to subtract the full amount, minus 8. Okay, so let's just pick one. Let's pick 10 because it's right here. When I subtract minus 8, what do I get? Plus 2. So let's pick another one. Let's pick a negative number. Let's pick, how about 3? Minus 3. 1, 1, 0. Oh, I gotta use an extra bit here. 1, 1, 1, 0. Now let me just put it as minus 3. It's below, so I'm going to add 7. So that's going to put me up to 4. Okay, so you get the basic idea here. The whole point is that it makes it really simple to implement a modulator in digital, because this is just wires. Your quantizers, wires, everything's wires. And my whole point was, when you feed this back around and you subtract, you're going to need to make sure that 2 words on the input back here are the same word size. So even though we show fewer bits here, N bits and F bits, you have to keep the 2's complement numbers the same. Are there any questions? Does it make sense? So if I were to give this on a quiz, no one would have problems. Evil chuckle. All right, and so here, if I wanted to implement a first order modulator, what would f of z be? Yeah. Why? Okay, so that's a good question. So, question I have is, why do I need that there? Why can't I get rid of it? What does it do? Tell me in 2 different ways. Why? If I just had a wire there, what would be the problem? There's nothing clocked in the whole circuit. It would just be an infinite, you know? Yeah, it would just go right around and back and out in an infinite loop. This says, okay, my word's coming in, word comes in, feeds back around, clock this, we go up, right? But also, does everybody agree with that? But also, I need that for the differentiation. So you remember, if I put this as z to the minus 1, and I take my input and feed it back, and then I feed it back around, what does that give me as a transfer function? Well, let's find out. V in, V out. So we get V in minus z to the minus 1, V out is equal to V out. And that says that wait a sec, something's not right. V out, V out, V in minus, well, let's see where it goes. So V in equals V out times 1 plus z to the minus 1. And that's V out. Now, I was going to say this is a differentiator, but obviously that's wrong. So I don't know what that is. It's not an integrator. It's not a differentiator. So how would I quickly determine what it is in my mind? No function where? Oh, yeah. Yeah. Well, I was thinking of just as a, yeah, you'd need to add the quantization noise in here. Yeah, let's not waste time on that argument. All right. Let's do one last thing here for this topic, which is just point out, there's our interpolation. If you want to interpolate to speed up, what's the simplest interpolation filter? Well, I would say the hold register. because you don't have to add zeros in the middle, so you don't need a mux. But the problem with a hold register is it introduces a sync response. So you hold that, your word comes in, boom, 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 right? And then you go to your circuit we just talked about, and then your DAC, if it's 1 bit, is just the digital output, an inverter. And then that feeds to your reconstruction filter, then smooths everything out, and you get your analog signal out. Anybody, okay, so in my mind, I'm like, damn, they should understand what this is. It's very clear. Anybody, is it not clear? So I'm going to ask some super simple questions here. So this is coming at a megahertz, and it's coming out at 120 megahertz. If I have a word that's coming in a megahertz, and the word just stays there for 128 clock cycles of the 128 megahertz clock, and the noise modulator is operating at 120 megahertz clock, this one's coming in as nice and flat and constant, right? So tell me what happens here. This is just you're holding the word steady for 128. What is this? What do you think of this as? So here I'm running this at 128 megahertz. This word's only coming in at a megahertz. So it's sitting there, oh, I'm slow. I'm sitting at 100, I'm going real slow. And this one's like clocking real fast, okay? So what is this filter here, this interpolation filter? It's a hold register. What is that frequency response? Yeah, it's a sync response. And if I want to get away from that, I need to do zeros padding, and then I need to multiply up by the interpolation rate, right? Then here I got my output, my noise shaping modulator, say it's 1 bit, goes to an inverter or 2 inverters, give you nice clean 0 and VDD signals. They have to be clean because they're not digital coming out of here, even though you could use inverters. Then I go to my filter, which could be just as much as simple as an RC. Any questions? All right, so let's see. We got a few minutes left. I'm not going to get to this topic here, which is the cascaded modulators, and I don't want to rush through it because it's super important for a lot of applications. So why don't we quit here, and then we'll pick that up on Monday. What should we have a quiz on Monday? How about something project related? Good? All right. Have a good weekend. We shall see you on Monday.